Hello, Professor. My name is Johan Rodriguez. My lab partner is Carlos Verdosca, and today I'll be presenting the drag race. So right now, we're trying to create a drag race using a finite state machine and statistic and edge-triggered interrupts. So as you can see here are all the ports I have set to. I have the RR LED being connected to PB0, the RL LED being connected to PB1, the GR LED being connected to PB2, GL is connected to PB3, Y2R is connected to PC4, YTL is connected to PC5, Y1R is connected to PC6, and Y1L is connected to PC7. Essentially, the R's at the end represent the side. So for RR, it'll be the right red LED, while the RL is gonna represent the right, no, not the right, the red left LED. Correct. Then if we see down here, the YTR is obviously going to be the second yellow LED on the right, while YTL is going to represent the yellow second LED on the left. And then we have right here, we have RB, which represents the button for right, the right button being connected to PA2, the left button, OB, being connected to PA3, and the reset being connected to PA3. So we also have all our defined statements here, like sensor port A, and we have set up defined statements for port A, port B, port C, and port D, which are all going to be used. We also have made sure to set up our system class, as well as have our interrupts, everything we need for our interrupts. So as you can see here, we also make sure to include two hex files, the st.int, which is essentially going to give us the uint32, which we're going to use for one of our variables later on. And also the second one, we have tm4c123, which is essentially going to be the hex file that provides us with maybe some of the information or defined statements that we do not have currently. It'll basically like fill it in for us. And as for the functions, we have disable interrupts, enable interrupts, and wait for interrupts, which actually do what they say. We've used these in the previous slides before. And the ones we should keep in mind are the port A init, which initialize the port A buttons, the port B LED init, and the port C LED init, which initialize both the port B and port C LEDs. The port G init, which can initialize the port E button, which in this case, it's the reset. Systic init, which is going to initialize the systic timer. The systic wait 500 milliseconds is going to generate the 0.5 second delay. The GPI port A handler and the GPIO port E handler are going to handle the GPI port interrupts for each of the ports. The systic handler, which is going to handle the systic generated interrupts, and debounce, which is going to be the debounce module for our button, because we don't want them to oscillate from 1 to 0. We don't want to get a random input. So as you can see here, we have our finite state machine right here. We have LEDs, which is going to represent what color the LED, it's going to take in the information from the finite state machine, and it's going to determine what color the lights of the LED should be. Then we have time, which is going to represent the amount of time that the LED should stay in that position, or how long they should stay lit. Then we have next, which is next for, and we have it for because since there's two inputs, that means that it's gonna two buttons, that means there's gonna be four combination of inputs, so that's why we have the for there. Then we have all of our 11 states. The first one, initial state, is when all LEDs are on. Then we have wait S, which is the waiting state, which is when all LEDs are off. The count Y1, which is the countdown Y state, which is when the Y1L and Y1R LEDs are on. Then we have the YW, which is essentially going to represent the countdown Y2 state, and that's when the YTL and YTR LEDs are on. Then we have the go state, which is when both the GL and GR LEDs are on, which essentially both green LEDs are on. Then we have the false SL, which is the false start left state, which is when only the R LED is on. The false start right state, which is false SR, and that's when the R LED is on. Then we have the false start both, and this is when both of the LEDs should be on. For in this instance, it's false B. Then we have the win left state, which is when the GL LED is on. Then we have the win right state, which is when the GR LED is on. Then we finally have the win both state, which is when GL and GR LEDs are on. Then you can see here we have our S, representing the index to the current state, and input, which is essentially going to obviously take in the input of the buttons to determine what's the next state the finite state machine should go. Then we have port A init, port E init, port A init, port B LED init, port C LED init, and system init, all our relationalized statements in our main. Then we make sure that the first state for the finite state machine is init, which is the initialized state. And then we have the wait for interrupt, so it waits for an interrupt. Then we have port A init. This is where we initialize, or we make sure that the PA3 and PA2 are inputs for our project. As you can see here, we make sure to make it priority 2, and we enable interrupt in 0, because obviously that's the interrupt that holds everything for port A. Then we have port D init, which is going to initialize the reset button, so whenever this activates, whenever this thing is turned on, it'll obviously go to the first state, which is the initialized state. And we make sure to have this set to priority 1, and make sure we enable interrupt 4, because that is the interrupt that controls all for the port E. Then we have our port C LED init. We make sure to set the system clock for that, and we have the port B LED init, and we obviously set the system clock for that. Then we have the 6-tick init, and we make sure to, once again, this is going to initialize the timer, and we make sure to also have this set to priority 3, as stated in the lab. Then we have our GPIO port A handler, and essentially whenever it detects an interrupt, so whenever one of the buttons is pressed, or in our case the switches are clicked, that means that it'll cause something. So for in this instance, whenever the left button is clicked, that means that it'll go to the false SR, which is essentially which is the false start right statement. If the right button is clicked, then it'll go to the false SL, which is the false start left. And when both of them are clicked, as you can see down here, it'll go to the false B, which is when it's false both statement. It's false both state. And as you can see here, we also make sure to have our depounces at the start of each if statement, so that whenever it does occur, it'll have enough time to like oscillate or it'll have enough time to oscillate everything, so it isn't switching from 1 to 0, and we don't get like a random input. We also have the same here for our port D handler. So whenever it detects this, it'll obviously, as you can see here, it'll obviously set the finite state machine to the first state, which is initialized state. Then we have our SysTick handler. As you can see here, the light port B and the light port C are going to receive information from the finite state machine to determine what LED should be lit up. Then we have our SysTick waits 500 milliseconds, and depending on the information from the finite state machine, it'll determine whether to wait for 0.5 seconds or 1 second. And we also have this input equals sensor port A to read the sensors, and then the S, then it's obviously, this next statement is obviously going to determine what the next state should be. Then we have our SysTick wait, and this is essentially going to help us with this is basically like setting groundwork for our SysTick wait 500 milliseconds. So essentially since we're assuming an 80 megahertz clock, this is essentially going to generate, since we put in this value, it's essentially going to generate a 0.5 second delay. So we use we're using the 6-tick wait to basically provide the ground for this. And then when we finally have our debound, we're essentially going to go for a certain amount of increments so that the project will have enough time. So unfortunately, I wasn't able to get the logic analyzer to work because it wouldn't accept the ports I wanted. However, I did manage to somewhat get the demo to work. So as you can see here, we're gonna load it all up. So as you can see here, you can take a good look at it. We have our right LEDs here. We have our right LEDs here. We have our left LEDs here. Then we have the first one right here is the right button, and then the left button, and then the reset button here. So we're gonna start this up. All right, hold on. So let's start it up one at a time. We get a better picture. All right, here we go. Sorry about this. So now we're gonna start this up. As you can see here, it goes to the first state. So if we were to click on the left button, it'll actually go to here, and then so if both of them are on, then it'll go to the green state. However, if one of them is off, or when both of them are off, they'll eventually switch off to the state. Like that. And whenever the reset is on, as you can see here, it'll go back to the first state, like that. And if only one of them is on, like the left button, and we were to click turn it off, give it time, and it'll go to the next state when the red LED is on. However, for whatever reason, even if one of them is on, it'll still keep going to the green state. I'm not sure why this is how it occurs. My partner was able to get it to function properly, but for me, it doesn't seem to work that well. Yeah, I'm still trying to figure out some of the bugs for this. But as you can see here, when they are both on, it obviously goes to the go state. And then when they're both off, it eventually goes off. Like that. So then, thank you once again. That was my lab. I'm sorry that I wasn't able to fix everything, but that's all I could do. Thank you, Professor, and I hope you enjoyed this demo.